So here we go. Okay. All right, so it's January 10th, 2020. And today we're finally going to start some trig. Really, really basic right triangle trig. And again, today's lesson is kind of long, but not because it is long, but because I do a lot of talking. So it's kind of a fun, this is my favorite lesson. So when I took trigonometry in high school, I didn't get it at best, okay? Did I still end up with a good grade? Yeah. But that's only because I worked really, really hard, not because I understood what I was doing, okay? You tell me something, I can spit it right back in any language, but no, I can't do it. I didn't understand it, and so it's really important to me that you understand why things are the way they are, okay? And so for me, you guys already have some background in trigonometry, but it was probably memorize it and then do it, not where does it come from and why. So you know something about right triangle trigonometry. SOHCAHTOA, did you know that? You've heard that? Yeah. Oh, that's what we're doing today. So write that down. SOHCAHTOA, yeah, sine, cosine, and tangent. That's where we're headed today. I write it this way. It's a little more meaningful. You should definitely write that down. Yeah, SOHCAHTOA. Okay. All right. So we really want to understand where that comes from, and that's what we're going to talk about right now. So SOHCAHTOA is where we're headed, and I want to tell you why. Because my question was, so SOHCAHTOA stands for the sine, cosine, and tangent ratios. But I always was like, when I was in high school, I was like, what is sine? What is it? I don't get it. Okay, this is what it is. So here we go. You do not write this. You can draw the picture. So this is the picture here. How many triangles do you see?
1, 2, 4. Actually, no, wait. 2, 4. No, wait. 1, 2, 4. Oh, yeah. 4.
Fingers.
3, 4.
How many triangles? 3. There's a little baby triangle and a medium triangle and a big triangle. Okay? All right. So, here we go. So, Amanda and her dog. Amanda. Yours truly. Okay. And her dog, my dog Cleo. Once upon a time, my dog Cleo. Stand in the shadow of a tall flagpole. So you are drawing this picture and you are doing the math here, okay? This is my tall flagpole. And I'm going to draw a little flag. Okay, so I got a little flag there. And I and my dog are standing in the shadow of a tall flagpole. Ladies and gentlemen, where do shadows show themselves? On the ground because of what?
The sun.
The sun, which is where?
The sky.
Over here?
No, other side.
Other side. Okay. So the sun was shining on this flagpole, and the flagpole lays a shadow down on the ground. Okay? And I'm standing here, right here. This is me. Once upon a time, curly hair. I used to wear dresses. Okay, and then this is my dog. Okay, so there's my dog. And all right. I'm walking my dog, and we're stopped because we have to wait for the light to change. Okay. So the top of my 6.5-foot shadow matches the top of the shadow of the flagpole. So my flagpole shadow is landing right here, and I happen to be standing exactly where the top of my shadow is lining right up with the shadow on the flagpole. And that shadow, my shadow, is 6.5 feet. And I happen to know that I'm standing 10 feet from the base of the flagpole. And the reason I know that is because I always have a purse, and in my purse I have a tape measure. I'm not kidding, because until last week I had a tape measure in my purse. My kids are too skinny to buy clothes for. So I actually know that my daughter's waist is 19.5 inches. And I have to go and measure all the jeans to see if they will fit her. Okay, so she's almost 11 and wears a size 7. And and they come up to like just below the knee. It's awesome. All right. So, all right, I digress. And that's why I get to that 31-minute mark. Okay. I am 10 feet from the base of the flagpole, and I am 5.5 feet tall, which is accurate also. And I want to know how tall is the flagpole. And so I'm going to call that Y, and I'm calling it Y because it is a vertical line like my Y-axis. Okay? Ladies and gentlemen, how can we solve for Y?
Use 10 times.
Okay. Nope.
Right.
Okay, stop. How many triangles were there? 3 triangles. They have a special name, those 3 triangles. They have a special name called what? They are right triangles. They are right triangles because they're perpendicular to the ground. So that's good to know. They are similar triangles. What makes them similar triangles?
Same angles, different
Same angles.
sides.
Okay. So the similar triangles theorem from geometry, ladies and gentlemen, is that if 2 angles are congruent, then they are similar triangles. And so when I look at my little triangle here, the triangle I form, I have a right angle, and I have this angle right here that is called the angle of elevation to the sun. And when I look at the large flag triangle here, it also has a right angle and that same vertex angle looking to the sun. Because we have 2 congruent angles, by default, do the third angles match as well?
Yeah.
Yes, they do. Okay, now clearly these are different size triangles, but by default, the third angle is also congruent, and that makes them similar triangles. Okay? Similar triangles have proportional side lengths. Proportion. So when we look at these triangles, I can create a proportion. So I can look at my height to my shadow length, and it should be proportional to the height of the flagpole and the length of its shadow. So the height of the flagpole, what's the length of its shadow? 16.5 feet. Okay, how do you solve for Y? Cross multiply. Can I just multiply by the 16.5?
Yeah.
Where did what?
The 16.5.
The whole length? Yeah. Okay. All right. So I'm going to go ahead and just multiply that 16.5 to the other side. So 5.5 times 16.5 divided by 6.5 and I get y equals 13.96, yada, yada, yada. So this flagpole is approximately 14 feet tall. Pretty reasonable height there. Okay.
Wait. So you still divided by 6.5?
Yeah. Okay. So then, how tall is the pole? It's not quite 14 feet tall. How tall is Cleo? So I want to find Cleo's height. I'm just going to call it C for Cleo. If Cleo's shadow is 2 feet long. So if her shadow is 2 feet long. So what can we do to find Cleo's height then? Another ratio, another proportion. So again, I'm going to use my numbers because they're nice. So my height to my shadow is going to be proportional to Cleo's height to Cleo's shadow. And again, we can multiply by 2. So 5.5 times 2 divided by 6.5 is 1.69, yada, 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 for Cleo's height, okay? And this is all interesting and well and good, but triangles were the foundation of math for a millennia before algebra even came into existence, okay? So we did counting and just adding and subtracting, and then there was this number 0 that came into being because before that we started with 1, all right? And then finally they're like, wait a minute, what happens, if I give you 25 rocks? So how many do I have now? None. I need a number for that. So then they create 0. And then after finally creating 0, which took a long time, then they're like, whoa, look at the sun. And then they figured out trig. Remarkable. There was some geometry and trig. Algebra came much, much later. Okay. So triangles were huge. And so they learned very early on that these we could have similar triangles and that their ratios we could use were proportional. And so, well, what we want to do then is actually look at these side lengths a little more closely. We're going to compare heights to shadows. So first, let's look at the flag. I want to compare the height to shadow lengths. The height of the flagpole was 13.96. The length of the shadow was 16.5. So that 13.96 to 16.5, I want to see what that ratio is. There is that 13.96 number in my calculator. It's nice and exact, so I'm going to use that. Divided by 16.5. And I get this crazy ratio, 846, Okay. Let's look at Amanda. Amanda's, mine, height was 5.5, and my shadow length, what was it, 6.5? Okay. So again, if I compare my height to my shadow, it was, hey, 0.846. Yada, yada, yada. That's kind of interesting. Huh. And then I look at Cleo. Cleo's was 1.96 something or other over 2. Okay, let me find that number. Here it is, 1.69 something or other. So I'm going to call it that number over 2. And, curious. What is it?
Is it because they're similar?
All, yes. So because they all have the same vertex angle. They're all similar triangles. It doesn't matter how big those triangles get if they all share that same angle of elevation to the sun. So you could add into this picture, you could add in like, I don't know, the tallest tower in the world. And if I compare that big giant tower to that giant tower's shadow length, what ratio will it give you? 0.846 every single time. No matter how small or large those similar triangles get, the same ratio, height to shadow, will always be the same. Craziness. Because someone noticed that those ratios, depending on this angle right here, those ratios, height to shadow, always are the same. We can use it as kind of a constant of information. And because they noticed those ratios are the same, they created the trig functions. Okay? They said, hey, let's give that special ratio a name. Instead of just calling it the height to the shadow length, let's call it tangent. All right? So when we use the words like sine, cosine, and tangent, they're really just telling us, so those, the words sine, cosine, and tangent are just telling us which sides of the triangle to use. That's all it is. All right, so those words are just telling us which legs to use. And it all depends on the angle theta that we are looking from. Okay, so this is, oh, and by the way, we just did height to shadow. All the ratios would be the same depending on the side length. So the hypotenuse to shadow ratio, the hypotenuse to shadow, the hypotenuse to shadow, those ratios are all the same. Okay, height to hypotenuse, those would be the same for all the triangles too. So all the different combination of sides all have the same ratios, and they noticed that, and so they gave them special names. So what I have here is a triangle. It's actually an angle. So you can imagine this is my initial side of my angle in standard position here. So this is my initial side, and here is my terminal side of my angle in standard position. And XY is a point on the terminal side of the angle. And what's interesting is if that line weren't there, I would have this point on the terminal side, and I could take any angle, put a dot on it for an ordered pair, and drop an altitude. An altitude is a line perpendicular to the piece it's landing on. Okay. And what we can do then is say, well, to get to that point, how many units to the right did I go? X units to the right. And then to get up, I went Y spaces upward. Okay. So this length of the triangle is X, and this height is Y. And I could place this point anywhere on here, right? So if I move it here and create an altitude, well, look, I just created similar triangles. So no matter where I place this point, don't I just have a bunch of similar triangles? Okay. And so it turns out it doesn't matter where that point is, because as we just said, those ratios are always going to be the same. So now we're going to give him some more information here. This length from the origin to our point here, I'm going to call R. That stands for radius, because eventually we're putting this inside of a circle. And once you have that information, now we need to know the opposite and hypotenuse and adjacent sides. So first and foremost, you're always going to label your hypotenuse. How do you recognize the hypotenuse? Opposite of the right angle. So the hypotenuse, always do that first. Label the hypotenuse. Now, the opposite side depends on the angle you are looking from. So we're interested in this angle right here, angle theta. The opposite side is opposite that important angle theta. So which side is angle theta? I'm sorry, which side is the opposite side? Yeah, so opposite that important angle is the opposite side. And that's going to change. If we were looking from up here, here would be the opposite side. Okay, so it depends on where you look from. Once you label the hypotenuse and the opposite of your angle, then you have the adjacent side. Okay, so we have our labels on. You know SOHCAHTOA. And again, I write it this way because it tells you that we have it in ratio form already. So here we have our 6 trigonometric functions, and you're going to start with just 3 here. Sine according to angle theta. The most important thing in trigonometry is the angle theta. Do not write sine without theta. Okay? So important. And by the way, this is not sin, it's sine E. There's an E on the end, sine. Okay? And your calculator button only had room for 3 letters. Therefore, they dropped the E. Okay? That's why. Sine of theta is the opposite over hypotenuse. So the angle is here, and our opposite side is y over the hypotenuse r. Cosine theta. Cosine, according to angle theta, is adjacent over hypotenuse. Adjacent over hypotenuse, or in our picture, x over r. Tangent, according to angle theta, is opposite over adjacent, or y over x. So I call these the big 3. Sine, cosine, and tangent are the big 3. Those are the 3 we're going to do first, always, always. And then to get a total of 6, we have their reciprocals. Okay, reciprocals. What are reciprocals? Inverses is better. Opposite means one is positive, one is negative. Those would be opposites. So reciprocal is flip the fraction. The reciprocal of sine is cosecant. All right? Cosecant. S-E-C-A-N-T. Cosecant of theta would be hypotenuse over opposite or r over y. All you have to do is flip the fraction. The reciprocal of cosine is secant of theta. Has a new name. That would be hypotenuse over adjacent or r over x. Just flip the fraction. And I bet you know this one. What is the reciprocal of tangent? Cotangent. Okay, cotangent of theta would be adjacent over opposite or x over y. Okay, once you know the big 3, the reciprocal functions are easy to get. Okay, now I'm always going to write them in this order. Okay, what you need to remember is that the sine function and the cosecant function are reciprocal. So how do you know that sine is reciprocal to cosecant? They all have a co. Sine goes with cosecant. Cosine matches with secant. Tangent goes with cotangent. Does that kind of help? Okay. All right. So you need to figure that out pretty early on, okay? But that's it. These are the trig functions that we're going to use today. Here we go. This is it, just so you know. Okay. There is a right angle here. Example 1. Find the value of the 6 trigonometric functions of the angle theta. Angle theta in the figure. You'll notice angle theta, different place, right? Angle theta is up high. That's going to change things around, so you have to be careful. Find the value of the 6 trig functions of the angle theta. That angle is the most important thing. I'm going to put a big star by that angle because we're looking from way up here. Okay, so if I want to find the trig functions, I have to have all my sides. So the first thing we need to do in this figure is find the third side. How do we find the third side? Pythagorean theorem. The Pythagorean theorem helps us out with side lengths. And ladies and gentlemen, this one example is like what we're going to do the entire semester. Okay? Find the third side and give me the ratios. So really important. All right. So the Pythagorean theorem is leg squared plus leg squared equals hypotenuse squared. So I'm going to call this leg x, only because it's horizontal like the x-axis. All right, so then what is 5? Radical 5, sorry. The hypotenuse. That is the hypotenuse. And I don't care which leg goes where, but we're going to do leg squared plus leg squared equals, the important one, radical 5 squared. So I have x squared plus 4 equals, what is radical 5 squared? 5, okay? And then I can move the 4 over, so I get x squared equals 1, and then take a square root, and x equals 1. All right, so x equals 1. Normally when we take a square root, we have to have a plus or minus, right? Yes, okay. But on this, not on this triangle. It's an actual triangle, so it has an actual length here of 1 unit. And then once we have that, now we can do our ratios, our trig ratios. So I'm going to do the sine according to theta and the cosine according to theta and the tangent according to angle theta. Very important. Before we write those down, I need to label my opposite and adjacent sides. So which one of these legs is my opposite leg? We're looking from here, angle theta, and the opposite side is 1, okay? So make sure you know where you're looking from. That leaves 2 as the adjacent. A-D-J-A-C-E-N-T. Okay, the adjacent side. All right, so Katoa, sine is opposite over hypotenuse, which would be 1 over radical 5. This is a great answer, except there's a radical in the denominator and we have to rationalize. I think this is a fine answer, but you'll find that it won't be on your homework or in your book. So we are going to multiply top and bottom by radical 5. 1 times radical 5 is radical 5. What's radical 5 times radical 5? 5. So this is the book answer right there. That is solving it. Cosine is, according to the angle, is adjacent over hypotenuse. So that's going to be 2 over radical 5, which you need to do what? Rationalize. So we're going to multiply top and bottom by radical 5. So I get 2 radical 5 over 5. Tangent is opposite over adjacent, TOA, T-O-A. So that's going to be opposite over adjacent. Opposite over adjacent, 1/2. And that one's good to go. Once I have those, the big 3, getting the other functions is super easy. Cosecant theta, secant theta, and cotangent theta are just the reciprocals. Cosecant is the reciprocal of sine. So we're just going to flip our fraction. 1 over radical 5 is going to flip and become radical 5 over 1, which is just radical 5. You'll notice I used the original one here that we didn't rationalize. If I had flipped this one, I would have to rationalize and reduce. Okay, so I like the original ones. They're easier. Secant is going to be radical 5 over 2, the reciprocal of cosine. And cotangent is 2 over 1, which is just 2, the reciprocal of tangent. All right, do you have any questions for me? All right, okay.